So looking over the homework, I noticed a couple of things. So I think there's a lot of confusion about what it means for what order means. There are two kinds of order in groups. So there's the order of a group. G has order. Say n, let's say G is a finite group. That means that the number of elements in G is n. That's simple. Like so, G group. And there's the order of an element. This is of a group. Of an element. Say we have an element X. And okay, there's a couple of different ways you can define it. There's a way that's sort of quick. This just means that you take the cyclic subgroup generated by X. It may not be finite, and you take the number of elements inside. That's equal to the order of X. Number of elements. Or equivalently, it's an equivalent definition. You could say the order of X. Sometimes you write it order. That's a lot of notation for it. But just you could call it the order of X. It's the minimum of positive integers n. N is a positive integer. N is a positive integer. Such that if I take x to the power n, I get the identity of G. Okay, so that's the idea. I assume that there's was confusion with this because some of the problems I couldn't understand that explanation because people would say things like the order of x is p. I looked at the one where it was prime power order group. An element has, so there's some element that has word. And people would say something like, the order of x is n, and let x to the n equal y. I would see things like that frequently. So I think that was a confusion about, if the order of x is n, then x to the n is 1. So that's like just the definitional thing. When I looked at, there were some issues, but I think it wasn't quite as bad. It was the one with showing that conjugation defines an equivalence relation, basically. And one thing I would say with that, which I saw, people seem to struggle with the reflexive property more than anything else. And actually, the reflexive property is sort of a different property than the other two, right? So if you think about, so we have for an equivalence relation, there were 3 different things, right? There's reflexive, symmetric, and transitive, right? And you'll notice with these two, symmetric and transitive, they are sort of implications. So you assume A is equivalent to B, and you want to prove that B is equivalent to A for symmetric. Or for transitive, you assume A is equivalent to B and B is equivalent to C, and you prove something, A is equivalent to C. So you have this if and then, whereas reflexive is sort of an existence kind of a statement. So it says A is equivalent to A, period, full stop, right? We're not assuming something to get there, it's just show that A is equivalent to A. So that's a different thing. So a lot of people in the reflexive part would say, assume something like A is equivalent to G, B, G inverse or something. But you don't show that there is some group element. So in this one, you wanted to say, just demonstrate that A is equivalent to A, this one. So you want to show that, A can be written. So you want to show there is a group element G such that A is G, A G inverse. That's what you want to show. want to demonstrate the existence of such a G. Of course, the most natural, easy thing is just the identity. Take G to be the identity. So you take G to be the identity, and you're fine. It works. E or 1G, I don't remember. We call it different things, but the notation for identity, if it's somewhere close, I'm happy. So that was something I also saw a lot of people kind of, I don't know. There were a lot of people that did great. I mean, I wasn't saying, I just thought, I mention it so that maybe. So another thing to mention, so I'm going to do the review today, but I'm going to do it online. I can't be at the office at the time. So today's review, same time, same Zoom location. But and if people, please, if you don't show up but you want some questions answered, please just send me a few questions. All right. Questions? I think today we're going to sort of wrap up sort of the abstract group theory part. Next, we'll talk about something more practical, which will lead to an application of this theory. Big area where people apply. So, but last time we had this proposition that I wrote down that I wanted to prove. We don't need to go through in gross detail, but let's prove a little bit of it. That it might have been. Let me go to last week's notes. Okay. Sorry, guys. Okay. We have this proposition, and we saw that this map, this F was a map. It was just a function. So I use map and function often interchangeably, but it's just a function. It's not a homomorphism. The algebraic structure is not really, something that really is compatible with F in a lot of ways, unless you have some condition. But we can say a lot about F depending on, various features of A. Okay. So let's see if we can prove a couple of these. Say, how about A? You can help me. This. And so I make coffee. I can't afford it. I mean, at the volume of my drink, I can't afford it. So I was really like low beans today. So I got weak coffee in my veins. Any help? Okay, F is injective, if and only if this is true. So what is F again? F is this map. Right, it just takes an element of H, an element of K, and multiplies them together. That's simple. So the problem like this, what I suggest is, we want to kind of say what, maybe if we start with F is injective, we'll say what the definition is. So F injective, if and only if, by definition, F of HK, H1, K1 equals F of H2, K2 applies H1. Well, we can even just say it, spell it out. H1 equals H2, K1. So, but we can take this equality, copy. This is true if and only if H1, K1 equals H2, K2. Okay, so now what do I do? This is kind of actually a bit of a trick. I mean, what we want to do. Kind of clever. one thing we can definitely do is we can start multiplying by inverses, right? This is like the only thing we can do if we have an equation. If we want to, well, not the only thing. There's one other thing we'll see in a bit. Okay, but we can. This is true if and only if H2 H1, sorry, H2 inverse H1 equals K2 K1 inverse. Just multiplied on the left by H1 inverse and on the right by K1 inverse. But now the trick is to notice something about this equation. Where is this? Where is it? It's in an H. They're both in H. You can multiply. I mean, you can take inverses in H. They're subgroups. H and K are subgroups. So you can multiply them, take inverses. This is an H. Where's this? In K, right?
Is that second K2 inverse?
Well, that's the thing, is that if this is true, the only way this is true is if this element, whatever it is in both H and K. It's in the intersection. Okay. So, but this implies H2 H1 inverse. Okay, I'm just going to write it again. K2 K1 inverse is an element of H intersect K. Supplies is equivalent to because I wrote the equal sign. Sorry, that's bad. Okay, so now let's go one way or the other. If H intersect K is 1, it's only the identity, then this is equivalent to the two equalities. Since these are both in H intersect K, we must have H2 equals H1 multiplying. I mean, that says that these are all equal to 1. So I can, and K2 equals K. Okay. If, on the other hand, HK just is bigger, so it strictly contains 1, then we can take H not equal to 1. G in the, maybe we shouldn't call it H, let's call it A. In the intersection. And just consider F A1G. So we can demonstrate an element, a pair, two pairs that are not equal as pairs, just go to the same point. So then it would not be injective. So what we're saying here is, if this is true, then it's injective. We get this property. If it's not true, then it's not injective. So they're equivalent. That's A. Now, I like C. C is really nice, and actually C has, if you ever study further on some mathematics at the graduate level or at any other higher level for algebra, you'll considering C quite a bit because this is a way to sort of reduce subjects from certain subjects. So let's take a look at C. I'll skip B. It says, okay, well, B is, it says that if the only way this is a homomorphism is if this is true. That's not hard to show. But I showed you. Yes.
Symbol in the previous proof, like H intersection K, something, the infinity.
It's just like a superset, like it contains, but it's not equal. So let's just say not equal to. I mean, it always contains. What the heck? Always contains. So let's just say not equal. I'm just saying there's some other element. And it's like subset. It's less than or greater than. questions though? Yeah, I'm used to certain notation. Of course, you should ask if it's something that's not. Okay, so let's say say H is normal, and we want to show that HK is a subgroup. So what do we need to show? That's one of the three things we need, right? We need compositions are in there. What else? Identity is in there, and inverse, right? We're asking whether HK is a subgroup. HK, as I said, this map is horrible in general. We just take two subgroups of G and we look at this map and we even look at this image. It just doesn't mean much. It's a bunch of cosets, just in general. But if we start putting some conditions on the groups involved, we can get something more from it. So if H is normal, we all of a sudden get a group as the image. It's still not a homomorphism, but okay. Okay, let's check. Is identity in there? 1G equals 1G times 1G, right? This is an HK. Good. Are inverses in there? So if HK is in, and well, let's see, then HK inverse is equal to K inverse H inverse. That's not obviously an HK, right? Any suggestions? The other thing you can do, there's sort of like two things you can do in the groups.
Is there H and normal? Can you just like put those? Is it commutative?
It's not commutative. Formality does not imply commutativity. It just means that the conjugate is in the subgroup. It doesn't mean it's equal to the element. So DA. So if I have a normal subgroup, let's just look at N normal. Means A is in N, G is in any element of the group. Then, so let's say N is in G. Then G inverse is N. It does not say that it equals A. That's not true. Just let it see. Not generally true, but it's not general. So we can't switch, but what we can do is we can look for a path for this pattern, right? We can look for this in here, hiding in there. The way we can do it is we can just do this. Famous do nothing trick. Do it all my life. I do nothing, then all of a sudden I get something. It's amazing. It's like inflation or something. This guy now is in H, but because this is a conjugate of an element of H, that's an H. And this, of course, is in K.
So are you conjugating by
K inverse. Yeah, that's actually something. Another thing I saw is in. I think this is in the problem on equivalence relation by this conjugation. That people when you did symmetry, there was something like this. I don't remember what. people were saying, okay, B is like this. I don't remember which one was it. And anyway, what I was hoping for is that people would write, and there were a few people that did write this. But you can see that whatever this is, you know, you're conjugating by that. So this is a conjugate of A by G inverse. Okay. Oh, let's see both. All right. So that shows us that inverses exist. Now we need the composition. And in composition, we do a similar trick. Now suppose H1K1 and H2K2 elements of HK. Then we can do H1K1, H2K2. I want that to be an element of HK. And again, you want to just sort of use this trick, which is that you can you sort of need to do nothing right in the middle here. H1K1. Oh, excuse me, not right in the middle there, not right in the middle here. Inverse K1. I just put a K1 inverse K1 in right in the middle here. What I can do, this is the identity, but now I notice that this is, I'll just put some parentheses around things. This, you can see I've got an element of H times a conjugate of an element of H, but that's an H. So this whole thing is an H. And then I've got two elements of K multiplied together. So that's still in. So you see normality actually really, I mean, if we use it in both inverse and composition, it's really a strong property. And we'll see it strengthening it more. Okay. So, that's what I wanted to do. I wanted to apply, pardon me. I want to apply this theorem. In particular, I want to look at this last bit. So this last bit tells us when we have an isomorphism. What we see in A, which we did prove, that this map is an injection if and only if the intersection of the two subgroups is 1. In B, it says that this map will be a homomorphism if the elements of H commute with those of K. Okay, so we get that. So if it's a homomorphism and if it's injective, we just need to ask if it's surjective. Well, if it's surjective, that's equivalent to saying that G is equal to all of these, all of the elements in the image. Surjectivity, remember, is ontoness, which means the range of the function is everything. So, well, the range of the function is H times K. And so if H times K is G, then it's everything. So this last bit tells us it gives us a way of detecting whether a group that we're dealing with is in fact isomorphic to a product of two subgroups. This is what it does. So what the business is all about at this stage here is, let's say I give you a group. Can you understand that group in terms of simpler groups? Can you understand and work with it in terms of simpler groups? So there's a nice example of this. So one application, I'll illustrate it pretty clearly. Corollary. We don't have a ton of groups that we're used to working, but one that we should start feeling pretty familiar with is modular arithmetic. Additive group Z mod n. So let's assume it say n and m are relatively prime, meaning their greatest common divisor is 1. Then I take Z mod n and I take the product group Z mod n, which is isomorphic Z mod n. Now why? Yeah, go ahead.
Is that commutative, so it would also be effective?
So all of the groups in this are abelian groups. Everything commutes. So these guys are commutative groups. This guy's as a commutative group, it's a abelian group. So yeah, you don't have to worry about normality. There's no subtleness there, and you do have from part B, you have this statement that if I can find these subgroups and I get all intersections B1 and everything, then I will have this. I will have a homomorphism because everything commutes with everything else. The proof here, which I'm not going to go into a ton of details, I'll just say some words. Is you can realize, so you can look at two subgroups. So consider H. You can add it a subgroup. I mean, everything's Z mod n or Z mod whatever is an additive group. So we'll talk about H equaling m times A, maybe a bar over it, and Z mod m. And here A is an element of Z. So all multiples of m. Take K n A. Z mod m. These are clearly subgroups, right? I can add, if I take two multiples of m and add them together, I get a multiple of m. So it's closed. 0 is a multiple of m, and negative. I have a multiple of m and I take its negative, it's a multiple of m. Right? So these are subgroups. These both are subgroups. Now you can, so I'm just going to say you can show H intersect K. Can you show it? Don't tell me why. Why is that true? Maybe my handwriting is pretty bad. So. Maybe I should write 0 bar. This is in Z mod m. Answer you guys a question. If I have a number, we call it C. Number C. I know 5 divides C, and I know 7 divides C. What can you tell me about C?
Multiple of 35.
Multiple of 35. 35 divides, because 5 and 7 are prime. Right? The two numbers and they divide a number, and those two numbers are relatively prime, then the product divides it. Alternatively, if I have two numbers that divide a number, their least common multiple will always divide that number. Two relatively prime numbers have least common multiple equal to their product. Least common multiple is the product divided by the greatest common divisor. So if I have an element of H, then I know it's the class of a multiple of m. And it's also in K, then it's a class of a multiple of n. So in other words, it's a multiple of m and n. So therefore, it's a multiple of mn. I take the representative. The multiples of mn are 0 in Z mod mn. I'm making that equal to 0. All multiples of mn. That's the 0 congruent. Like that. So that's the proof. So you can show this, and this is this part 1 of that proposition. And then also you can show HK. So you can show this, you can show HK, and here you would write H plus K because the operation is addition. This is equal to Z, to all of Z mod n. And the reason for that is Bézier's, because they're relative. So there is some A and B, so that AM plus BN equals 1. That's that theorem we had. So of course, if we do this, we can do this with classes. So 1 will be in whatever this is. But if 1's in it, a cyclic group generated by 1, we can get everything else. So these two properties here are the two properties you have in part 4 that say that there's an isomorphism. Okay, let's see it in action. I'm going to build up like a big library of these guys. I'm going to do, I do like damage these, so I don't want to keep the originals. Future torture of later generations. Okay. On the left is Z mod 6. The multiplication table is Z mod 6, right? I can take, it's a cyclic group generated by 1. If I add 1 to anything, I'll get, 2, 3, 4, 5. And then once I add 1 to 5, I go back to 0. Cyclic groups have this nice kind of pretty structure you can see in their multiplication, table. It's kind of very simple. Nothing complicated at all. But you can all of a sudden look at Z mod 2 plus Z cross Z mod 3, which are pairs. They're pairs of an element in Z mod 2 and an element in Z mod 3. And so they look different. They really do look different. Okay. But look at the pattern. You see that this pattern is exactly the same. The structure of addition really behaves precisely the same. So the ordering of the table is set up to ensure that, we map just this way. I guess I skipped 2, right? That we get an isomorphism between these two groups. The algebraic structure is really identical. It's a very useful thing, actually, in higher math to be able to do this kind of thing. Is to take a group that's kind of complicated. Of course, Z mod 6 isn't that complicated, but other groups that might be complicated, and break it up into pieces that are simple. Think of it as like a molecule versus atoms. I don't know how you want to think, but it's a very much a procedure we do in math to try to classify things. There are certain groups, like Z mod 2 and Z mod 3, and a bunch of other ones, that are simple, like most fundamental groups. And other groups are all built with them. Simplified in various ways. Identical, and in fact, they've been fully classified with finite ones. As I said, I think I've said this. But this is one way to break a group up, is to sort of look at it as a product. All groups are products. Okay, guys. So now, questions? All right, so now I want to so Arden actually says something funny in his his preface or something to the book, where he says, I wasn't even going to include quotient groups because this is sort of designed for undergrads. And, I don't think they're that important. He's like, but then, every algebraist in the world would like to send me hate mail or something. I felt like I had to do it. I don't think I agree with that.
I mean, I wouldn't send them hate mail, but
I
I don't agree. I do think they're kind of important if you're trying to understand how to deal with groups. But I get his point. They're not like, they're just another construction at some level. It's not
if you're what you're interested in is sort of getting to applying groups to understand. This could be bad.
I might run out of batteries. If I run out of batteries, I'll go to the board. So yeah, if you're trying to understand
Groups and how they act on things.
maybe quotient groups aren't the most important thing, which I think is what we're trying to get to. But let's define it so that you guys are
Well-rounded in your understanding of groups. Okay, so here's the theorem. So this is quotient groups. So what do we know? We know that if we have a subgroup H and G, then we have this quotient map which sends G to the left cosets of H.
set of left cosets.
And it just takes an element of G and it sends it to its left
Left coset.
That's all it does. Right. So it sends A to A times H. There's a map like this is surjective. It's on 2, right? Because everything in here is on left coset. And this gives us a nice partition of G, the left cosets partition G.
We don't have any algebraic structure over here. Not a priori.
It's just some set.
So what quotient groups say is
If we add this normal condition, we do have algebraic structure of a G mod H, and furthermore, this map 5 then becomes a homomorphism. So that's what we want to show. I'll just call it a theorem. So if N is a normal subgroup,
which
has this notation of this kind of like triangle. Subgroup. Then I take H here. I have 2 left cosets. I multiply them together. To A, B.
it is a left coset.
Which by itself is not.
Clear, but furthermore, it's the left coset with representative AB.
And that's a group of this operation. Off composition. Furthermore,
Quotient map is a homomorphism.
it's not hard. So I'm just going to prove it by saying, so you can, I'm going to let you play with this as much as you want, but what the important part of this theorem is that this is independent of
The choice of A and B.
right. Cosets, when I write AN, I could have written it as some other element times n, right? So all like anything congruent to A mod n, I could have written that. So there's ambiguity. There's ambiguity.
This doesn't really make sense for an arbitrary,
Subgroup. Yeah. It's a normality that makes this make sense, and that's what I want to show. I'll show that. Let's suppose A1n, A2n, B1n, In additive, in modular arithmetic, this would be like, you know,
I'm saying, 7 and 2 are equal mod 5. So I can write the congruence class as 2 plus
5z or 7 plus 5z. Doesn't matter. It's the same congruence class. It's the same.
So I want to show then that I want to show that A1, B1 and it is A2, B2. And then this is equivalent, we've shown in the past, this is equivalent to A2
Inverse A1, B2. I'll say then this is equivalent. Okay. Let's make an observation. So but observe. A2, B2 inverse A1, B1. This is equal to, okay, we can just B2 inverse A2 inverse A1. Let's do nothing again. I'm going to do nothing right here. The identity right there. I do that,
put parentheses.
around this. Now, this element, B2 inverse B1, is an N. Here. A2 inverse A1, this element. Right here. And I'm conjugating that element by B2 inverse B2.
Since N is normal, it's an N.
I've got two elements in N. N is a subgroup. I can take their product. This is in N. So what that means, again, this equality, something inverse something else being in the subgroup, is equivalent to the left cosets being equal. So A1, B1 is A2.
That says that's proving that this is a well-defined operation.
Yes.
Why is that the same thing again?
Well, if you want, you can just, let's look at this one. These two sets are equal, means that if I take A2 inverse and multiply on both sides, here I'll get A2 inverse 1 or equals N. Okay. So that means that if I multiply by 1, it must be in it. So that's one way. And then the other way, I think we've proven this in the class. Yeah, it's one of the earlier propositions that left cosets being, I think in the section on left cosets being equal there's an equivalence relation, which is this equivalence relation, which some people put into the problem on congruence. So, but that's a different equivalence relation. My iPad doesn't like it. All right, I'm going to drain this battery. Let's see. So we have so as I said, you can go ahead now. What has been shown here is that this multiplication is not ambiguous, like it is well defined. And so showing it's a group is quite easy, right? So observe to see it's a group. It's a group. Well, you just notice that notice one 10, or just N is, I just say N is the identity. because it has the representative 1. So you just put in 1 for B here, you'll get AN times N. It's AN. That's an identity. And inverses exist because AN inverse to A inverse. Again, using this property, multiply the representative. Associativity follows just from the associativity of the product in G. Not a subgroup of something. It's a group. What is it a group of? It's a group of subsets of G. Got these big partition subsets and you're multiplying them together. The other subsets. Okay. It'll work. Now, why would you do this? Well, as I was saying, this does kind of talk a little bit about shadows. So you can definitely talk about, there's silly things like this is a group for which, if I mod out by this group and I take the number of elements, you get division. So there's kind of things like that. If you like to understand the basic numerical invariance of your group, this is something that comes out. But furthermore, there's this theorem, which is not hard to prove, called the first isomorphism theorem. Maybe you guys will like this. Maybe you won't. There's also a second and a third. Kind of a fourth. You won't do those. So it just says, if I have a relationship, say from G to G, given by homomorphism, then the image group, this is a subgroup of G prime, of G tilde. This is a subgroup here. This is isomorphic G mod kernel. So the kernel is always a normal subgroup, as we've shown in class, of the homomorphism. In fact, it's a very good one to understand because if I quotient the group by that kernel, then I get something isomorphic to the image. So in particular, if P is on 2, it's projective, then you get the isomorphism P itself, which is the image of the homomorphism. It's a quotient. Meaning if you have an onto homomorphism, you know the group you're mapping to. I mean, all of the information about the group you're mapping to is contained within the group that you had to start with. You can construct it by just quotienting out by a subgroup. It gives you the structure of kind of where you're going. Of course, a lot of homomorphisms that are interesting are not onto, but are not surjective. But okay, that gives you a sense. And a way to prove this is just to factor this map. It's a proof. It's just you take, and I'm not going to, I don't want to bother you too much with details. This is not, it's not that hard. It's just a question. You consider both maps. So you got this phi and you factor by considering this quotient map. So you can quotient out by any normal subgroup you want. So we'll quotient out by kernel phi. And then you produce a map here from G kernel phi, mod kernel phi to G, to script G, that makes this commute. In other words, that makes it say that if I start here, here it's the same as going like this in composition. Then you can just prove that this map here maps isomorphically to the image. If not, so construct this. It's not a part of construction. Just say ascending. So, a coset, A times kernel phi, coset, eBay. That's a definition. We show this is a one-to-one map.
So it gives you a Mortisman's image is the image of the.
So that's nice. So I had a couple of examples. Of course. So why do we have the notation? Yeah. So examples are, let's look at here. Oh, we're out of time. So maybe 2 examples. Quickly. In an abelian group, every subgroup is normal. So we have NC is an abelian group of C.
C plus.
So we can form the quotient group. And that is
Really equal to
C, what I've been writing as C mod N. The notation a lot of people use. Other with the Z. So this is a quotient group. And another example that would be really nice to think about is we have the set of even permutations, which we call the alternating group. That's a normal subgroup inside of the symmetric. And what's its index?
how many cosets? 2. Right, they're even or odd. They're 2 cosets. Permutation either be odd or even.
So this has index 2. So you can form the quotient group Sn mod An. And this will be like a group, I mean, it's C mod 2, or you can think of it as 1 and minus 1. If you're thinking multiplication. So, and of course, there's a lot of other ones, but
We don't have time, so we'll talk about. We probably won't talk much about those, but okay. All right, guys. So next time we're going to start with some linear algebra. I'll be online at 3:30. So please
join if you have some questions on the homework.
how's it going?
Sorry to understand.